Alice and Bob have a secret love. In order to keep this from her parents, Alice suggests that she send messages to Bob while binary codes. Bob needs to learn the binary string first, every time before he decodes Alice's message. The first string is like this. This one is easy, right? It's just a repetition of zeros. Then, Alice tried another one. This one is harder, but not bad. Bob can describe it as a 24-bit string with ones in odd position and zeros in even position, and Alice sent her third message. Maybe Bob can only learn this string bit by bit. There is no easy way to describe this string other than write it down in its original form. How hard it is for Bob to describe the existing string depends on the complexity of the string. The complexity of describing a piece of binary code or text or any object is quantified by Kolmogorov complexity. Kolmogorov complexity is the length of the shortest computer programs that produce the object as output. It is a measure of the computation resources needed to specify the object. Kolmogorov complexity has lots of applications in physics, computer science, math, biology, and so on. For example, we may want to know the complexity of a piece of genes sometime. Unfortunately, Kolmogorov complexity is not a computable function. You cannot come up with an algorithm that easily outputs the Kolmogorov complexity of arbitrary objects. In some practice, people quantify the complexity by how much you can compress a given object. This is common in the study of genes. Kolmogorov complexity is also known as algorithmic complexity. We have been talking about describing a piece of information, and you may already think of Shannon Entropy. Especially Shannon Entropy is more widely used. Yes, Kolmogorov complexity and Shannon Entropy are connected. Both theories provide a way for measuring information, and both use bit. However, they are different. In some sense, Shannon tried to characterize the source that produced the object, while Kolmogorov complexity characterizes the object itself. For example, we flip a coin. If we get head, we write down 1. If it's a tail, we write down 0. The Shannon entropy is at most 1 bit. If it is a biased coin, like it's more likely to produce head than tails, then the entropy is smaller than 1. However, Kolmogorov complexity focuses on the binary string we write down. It could be arbitrarily high if we really keep writing down a random string. It's not about the coin. Shannon cares about the information that one random variable carries about another, while Kolmogorov studies the information one sequence gives about another. In an appropriate setting, the former one can be shown to be the expectation value of the later one. You can find related research on that, but I won't go further at this aspect. In my quantum machine learning project, I study the minimum resources required to learn a certain binary function. The goal is to describe or reconstruct the function. So I use Kolmogorov complexity. As we mentioned, it's not a computable function. So how did I find Kolmogorov complexity for a given function? Well, I'll see you in my next video.